And we can get started. Great, thanks. Happy to have so many people here. And we'll touch upon the bold question of whether we can automate supervised machine learning. Specifically, we'll talk about this tiny step, important step of tuning the hyperparameters of the models automatically. So to present myself a little bit, I'm Thorben Jensen. I'm working for this company, Informationsfabrik. We love data. We're based in the beautiful city of Münster. And we're happy to support a larger number of clients to scale up data science and bring it into production. So this is sort of our passion and our mission. And yes, and while we do this, we notice several things. One of them is finding the optimal hyperparameters of our models is important. And this being said, you might ask yourself, some of you might ask themselves, what is a hyperparameter though? Let's ask Wikipedia. It is hyperparameters are parameters whose values are set before the learning process begins. By contrast, the values of other parameters are derived via training. One example would be the depth of your neural net. You don't train that during the training process, you set this before, a hyperparameter. And there's many others. Just one example. And before we dive into algorithms for automatically tuning these, I want to take one step back and talk about where we are located in the pipeline, what we could call the pipeline of supervised machine learning. You start with an idea and data, you visualize your data, you pre-process it, build your features, and then you're tuning and selecting your models. This is what we are going to talk about. This special boxes we're going to talk about today. Afterwards, you want to stack your best models, deploy them, and monitor them when they're live. So these are the steps we focus on the central box. And also to frame the problem that we want to tackle, to make this clear to you, I prepared a week in the life of a data scientist for you. So let's look at this example. So you start your week tuning your model. And to be honest, it's fun to explore how the hyperparameters change the behavior of our models. It's a good thing to do. At some point, when you think you're done, someone tells you, well, then now there's much more data, and please also use this data for your model. For you, that means you have to go on retuning your model. And, weeks, Thursday is approaching, Friday is approaching. When you think you're just done, someone tells you, yeah, this one variable that you think everything depends on, please remove that. And now you have to go on retuning your model, and maybe it's the weekend already. So that's the problem that we're tackling. Understanding hyperparameters is cool, but, well, maybe we want some weekends off too. All right, so for tackling these problems, the first steps, I think many of you are familiar with, are grid search and random search. Grid search is simple, but I'll iterate a bit how it works to make a point. Grid search, you select the values that you want to test for specific hyperparameters and try out all the combinations. As an example, here in a two-dimensional space, this would look like this. Parameter 1, parameter 2, 3 values each, 9 combinations. Looks like a chessboard. This looks fair and efficient. Actually, it's not so efficient because one of the reasons is that hyperparameters in their effect on model performance, they do vary. This is visualized here on the left. Parameter 2 in yellow. It's not so important for your model performance. Well, however you set this parameter is not so important. Parameter 1, however, see this peak over there, the green one? This is where parameter 1 would boost model performance. This is the crucial point that you would like to find. Problem is with grid search, you're not testing each parameter at many variations. You end up only testing 3 variations. This is where you miss, in this example, you miss this peak. And this is quite likely to happen in grid search. To the rescue comes random search. In random search, well, you won't have to sample more often. You just sample randomly over an interval for each hyperparameter. Same example here, same situation. You sample 9 times, but now your coverage of this important parameter, parameter 1, is much higher. You actually get the peak right here. So that's great. Now we see this is one of the reasons why random search is also, for not just for this example, for many other examples, more efficient at finding good hyperparameter combinations automatically compared to grid search. Some of you might have read about this already. Now, actually, we could now stop this talk and say, okay, we have a tool that helps us.
But the problem is, like, how could it determine, like, because of the randomness, like, is it mainly because of hyperparameter 1 or hyperparameter 2? So, like, it could be a bit ambiguous, right?
Yeah, let's just discuss this in the end. Sorry, and thanks. I think there's one limitation left here that should be tackled. We choose new hyperparameters, and at this point, after 9 samples, we got a nice understanding already of how a model might react to our hyperparameter setting. But random search would now just randomly select new hyperparameters for us to test, and we go on testing randomly. I think it's quite a waste of information because we already have some information. We want to use this information. If we want to use the information from the previously tested hyperparameters, now there's many options. And I'd like to talk about one option, one class of options that is not just promising and popular, but also like personally quite a lot. And this is the family of sequential model-based optimization, a type of hyperparameter optimization that uses all the previously tested hyperparameters to propose new hyperparameters. It's not a model-free optimization. A random search could be you could call it model-free. You just test randomly. In this, you optimize randomly. In this case, you use a model for optimization. You already have your machine learning model. Now you use another model that will predict from a given architecture, one hidden layer, you get a certain model performance. More hidden layers, you get another model performance. You could get this from your original machine learning model too, but that's slow. You take another one, a smaller proxy model, that predicts the model performance from the hyperparameters. And for this class of these algorithms, they're also labeled Bayesian optimization, but we don't need the Bayes right now, so let's cut it out from the talk. They use a fast regression model as a proxy for your slow machine learning model. They more or less take out the same steps that I'm presenting now. So first you could start by evaluating some random set of hyperparameters. What we did before, we had 9 samples. Okay, gets us started, we have first data. From this first information, you build your faster, smaller regression model, this proxy model, for predicting model performance from your hyperparameter. Now you have this model trained. Because it's fast, and you can quickly probe this model for suggesting good hyperparameters to test next. Test the models. If it's a closed form solution, it will give you instantly. Otherwise, you'd have to search within the model. And it will tell you, for your original machine learning model, test this parameter, because I think it will be very good. And this is what you can do next. Then you evaluate your original model with a proposed hyperparameter. This is slower, but it gives you real-life insight, gives you more information. Now you have another sampling point, another hyperparameter tested. You can update your faster regression model, your proxy model. And this is sort of a conversation between these two models. One proposes good hyperparameters, next one tests it, and so you don't have to run your slow machine learning model, your original model, with just maybe not so promising parameters if they just be random. I'll mainly talk about 3 popular options for building these fast proxy models. That's the Gaussian process, random forests, and tree structure parser estimator. Let's start with the Gaussian process. Let's take as an example a maximization problem where there's a true relationship between a hyperparameter that you vary and the model performance shown there in this dashed line over there. You have 2 points sampled. These are the black dots. For 2 points, you've sampled your hyperparameters and know sort of the truth, how your model performs at these settings. Now you fit the Gaussian process to these 2 points. You get a mean expected value. That's the solid line. And you get an uncertainty range, the blue range. What you want to get next, if you're maximizing, you're looking for a relatively high expected value, but also high uncertainty. So there's still some room for improvement left. This is where you sample. This intuition of combining these, the expected value and uncertainty, is formalized in the acquisition function. Here visualized, you would sample at this red triangle. This is what you do. You get more information, you find out, oh, for this hyperparameter, even though promising, we're not optimal yet, but at least you get more information. And you get the next recommendation, where to sample next. So this is how it works, sort of in a nutshell. And now let's look at the Gaussian process doing exactly this in a nutshell. On the right, you have a true target function. And on the left, sorry, there's actually the sources. Sorry, I have to say this. There are sources from nice blog posts linked in these pages, but the beamer doesn't show them. You'll find them online later. They're on the right-hand side. So I'm stealing a lot of brilliant blog posts, but I'm linking to them so you can dig deeper. Sorry, just remember. All right, on the right-hand side, you have the target function, two-dimensional hyperparameter space. On the left, you have, based on these 5 initial sampling points, you have the Gaussian process reconstructing this original function. And we see it in action, adding sampling points. And we see, first thing we see this reconstructed Gaussian process sort of converging towards this original target function. Also samples more in this area, which is a good trade-off between exploration and exploitation. You're looking for an optimum here, you're maximizing in this example, so you're sampling more there. It's quite efficient. So that's the Gaussian process. Let's look at the random forest next. The random forest actually does very much the same thing, so I'll be a bit shorter here. 2 main differences still are. You don't use the Gaussian process regression, use a decision tree ensemble. And 10 trees, already enough to do this. One major advantage here of the random forest is that you can, in your model that predicts from your hyperparameters, model performance, you can now integrate categorically scaled parameters. For example, the activation function of a neural net. If you want to combine this, if you model the interaction between that and the learning rate, and not separately, you might want to look at the random forest there. So, well, the rest is more or less the same. Finally, how does the tree structure parser estimator work? Again, a simplified example. So from an initial set of hyperparameters that you test and the model performance, in this example we're minimizing, we have a loss that we want to minimize. We're separating between the best ones, the best 20% in this example, and the rest. So we create 2 classes, the red ones and the blue ones. We want to find new hyperparameters that will end up in the red group. So for suggesting good hyperparameters that will end up in this group, we model the probability with a Parson estimator. We model the probability for new hyperparameters to end up in the red group, this curve, and the blue one, this curve. These vertical lines will be random suggestions of what next hyperparameter to sample, and now these random suggestions, we like to score or see how much expected improvement we get from these. And for that, we can simply divide the probability to be in the red by the probability to be in the blue, so expected improvement, and we find that this one here is quite promising, quite likely to be in the red group. So this is how it works. It actually does this separately for each hyperparameter. All right, so much about the algorithms. And before we score them, before we show our benchmarking study, I'll first like to compare them more on the conceptual level based on what we know so far. So we might have some criterion, some things that would be useful for us when we use them. So maybe we want to make sure that our optimization algorithm takes care or also pays attention to the interaction between hyperparameters. If we just change this one hyperparameter, set it to the other one, maybe it's not so efficient. We want to take care of the interaction. And actually, the tree structure Parson estimator does not do this well. You also want to include discrete hyperparameters and the Gaussian process has some limitations there. Next criterion might be you want to have it easily configured, because the worst thing you need for tuning hyperparameters is an optimizer that has some hyperparameters, again, that you need to tune. How do you do that, right? Problem is the Gaussian process has some problems there again, because you can really break it, and we did that just configuring this one parameter not so ideally, and it didn't help us a lot. Random forest is okay, random forest is quite stable, and the tree structure parson estimator, very easy to configure. And finally, you might want to have a Python library that you can just import instead of re-implementing papers from scratch. You got it for all of these. And now you can take your photo or watch it later. Well, happy to help, right? And now I think we're set for looking at our benchmark studies. Just a small study that we'll first present, and then we'll back up with some insight from the literature, because I guess just one study would be a bit biased. So we're benchmarking. So we benchmark set algorithms with the libraries you see there. Also as a baseline, we have random search as a baseline, and we have a human expert from our team, which is, I think, very proficient in tuning the type of model that we're using. And that's actually an XGBoost. And if you might be using neural nets, we did it with XGBoost, decision tree ensemble. We used 16 core CPU machines on varying random seeds, etc. Several weeks of runtime. And 2 data sets. First, Iris, because it's not a real machine learning study if you don't use Iris first. Second, we had a real-life data set we wanted to test on from the insurance world. And so 2 limitations I think are worth mentioning. First, it's only 2 data sets. You want to scale it up to 50. I see studies that use plenty of data sets, so this would be better. The second one, we're talking about algorithms before. Now we're benchmarking libraries, so we're comparing actually 2 things. Some of these libraries, if you look at their papers, they're paying close attention to very maybe important technical optimizations that other libraries might not do. So we're varying 2 things at the same time. Maybe not so ideal for a benchmarking study, but it's also more real life. And then let's look at our first result on the Iris dataset. What we're tracking is the average best result that we're getting over time from the algorithm. So average means over different random seeds. And our results would look like this. We have all of these algorithms quickly improving on performance and then saturating. We have sort of a baseline. The random search sort of shows us the top here. Others are better. Specifically, the random forest and the tree parson estimator did well. So this was over. We'd have to discuss this later. For timing. So this was over several random seeds. Now, for one random seed, we compare to the human expert. So I'm curious what you're thinking, what you're expecting for this data set. The machine wins, and the human only got this far, over 3 times updating the hyperparameters. Well, that's just one random seed. So for a real-life data set, giving the same visualization, we see something similar. First, rapid improvement, then some saturations, however, on the same level for all of these algorithms. They do differ at the speed. And the smack shines here. I was wondering why, looking a bit closer at the logs. Turns out that their starting point is just lucky. It was very close to the optimum. And that's also, well, it's okay to be lucky sometimes, but it's probably helpful for you to know why. Even though still SMAC is a good optimizer. Then again, tree parson estimators under the top 2, but well, it's a bit blurred here. All right. Compared to a human expert now, human expert also got to this level here. So probably a data set, maybe maybe a random seed at which it's easier to find an optimum here. That's real life, right? And I'd like to add 2 studies from the literature, just to like quick spotlights from the literature where something similar has been done. And there's one example where the Gaussian process was shown to beat random search. So how did this happen? In the beginning, they were not very different. But at some point, I think that's the point in time where the Gaussian process has enough information, where it can start to make good guesses, understands the hyperparameter space well enough, becomes better than the random search that just goes on randomly. Next, insight from the literature, one example where a tree structure Parson estimator beats the Gaussian process, random search and manual search in the very end of such a timeline, again, over time, plotted model performance. All of these, the 3 other ones sort of end up at this level, and in the end, tree Parson estimator kicks in and improves over that. So this is a variety of results here that I'd like to condense a little bit in and take home messages, and I'm welcome to discuss this later. So many people here will have a good discussion, I hope. So my personal take-home messages here is, first, more free weekends means it seems to be possible to use automated hyperparameter tuning, seems to be better than manual tuning. So more free weekends. These sequential model-based optimization algorithms do not differ much in performance, actually. You have several benchmarking studies, and sometimes this one is better, sometimes the other one. We couldn't clearly distinguish them in our study ourselves, but they come with different constraints, and this might be more important when you apply them. Some they have different capabilities of cope with different scaling of your hyperparameters. Think of Gaussian process that likes more to use continuous hyperparameters. Modeling interactions between hyperparameters can be important, and there's definitely many examples where that is the case, and that would be a problem for the tree structure Parson estimator. And finally, as said, some of these algorithms come with a large number of hyperparameters, and these might have to optimize again at some point. So it's a bit ironic. Huh? You have this machine learning model on top with hyperparameters, uses the hyperparameter optimization on top with more hyperparameters. So what to do next? Huh? It's a philosophical question I have to leave open for you. Then we've seen that the tree structure Parson estimator is simple but surprisingly effective. It's quite cool. Next, we've seen the random search being simple, but it's actually quite scalable, and it's also reasonably competitive. So not too bad. Finally, to sum it up maybe, it's my personal take-home message is to spend my time wisely. And instead of manually tuning my models, I guess in the future I choose more to get more data and create more features, spend my time there, because from the manual tuning I'm not expecting so much benefit over an automated approach. All right. So these are my take-home message, but before we can start the discussion, there's one more thing we need to do. We have to take this step back again, because we started with a question about, can we move with this towards automating supervised machine learning? Thanks to the $1 million question, even more. For this central box we've talked about, I'll give a check mark based on what we've seen. So it seems to be possible to automate it to a very high degree. What about the other boxes then? Let's move a bit downstream, this pipeline. For stacking models, we see nice ways to automate it. I'll be very brief here, and we have to talk about all this probably later. For stacking models, we see nice framework that automate this for us. And actually, these 2 steps together work very nicely in frameworks. Think of H2O AutoML or the large number of other libraries that are available there. When it comes to deployment, we have modern DevOps that help us automating deployment of these models. So this, I think, also gets a check mark. When it comes to monitoring models in the wild, personally, I'm not aware of a tool that would capture all my requirements or fulfill all my requirements for sending a model out there into the wild and have it monitored and be sort of applied safely in an automated way. I don't know, maybe if you know, please let me know. If we move upstream a little bit more, pre-processing gets a check mark, but only tentatively, because I see nice libraries popping up like feature tools and Tpot that automate parts of feature engineering. I think in 2 years we'll know more what we can do with these and what's still left out there. We'll get more insights there, I think, in the near future. Many people's working there. It's sort of the new frontier of automation here. And these first steps, I think automation is very different there because basically you need to know your data, look at it, and have a good idea what to automate. Makes me think of Pablo Picasso, who was quoted to say, "Calculating machines are useless, all they give is answers." And maybe you could take from this the fact that you don't get the right questions that we need for good data science. But maybe it's not true anymore. I don't know. Happy to hear your opinions. So finally, thank you, and thank Tobias and Prasan for supporting this study. So that's it from my side.
Thank you very much for the talk. I think it was very interesting and very condensed, a lot of information. Cool. So we have quite a bit of time for questions, which I think is a good thing. So let's go for it.
Again, thank you very much for the talk. Great presentation. You mentioned in just one phrase the word Bayes.
Yeah.
Can you talk a little bit about that and the link with these 3 different methods?
Yeah. Actually, you get me sort of on the wrong foot because I'm more like the frequentist guy and not the Bayesian guy. I mean, the idea of Bayesian is using a prior for prior information, and then when more data comes in, there would be more hyperparameters being tested. You can update the model. So this idea of updating this proxy model is very Bayesian. So now, what's your prior? You could actually draw your distributions of hyperparameters that you find promising, and some papers do this. And this would make searching more effective. If you'd be like Google, that gives provides model training as a service and see lots of different data sets, you will have very good priors for knowing what hyperparameters to set when data looks like this or that.
So you can accelerate it even more.
I think with the prior there, a predefined prior would accelerate finding good hyperparameters. That would be the Bayesian idea, if I get it right, but no guarantee because now anyone who disagrees has to speak up.
Thank you for the great talk. Quick question. The scores that we were seeing in the benchmarks, were those average cross-file scores or were they actually out-of-sample scores? Because I've seen in a few tests that one can start kind of overfitting the cross-file score, even though that sounds absurd, and then the out-of-sample scores didn't actually correlate with the cross-file scores anymore. And
it's just a cross-validation. So you can actually overfit the folds there, yes.
So also on this evaluation, so if you take Iris or whatever other data set you had, and you have a highly flexible model which has a nonlinear loss and many possible configurations for optimization. So you said at one point sometimes you only took one random seed and sometimes you took several to evaluate if you could basically with any random seed and some kind of random process to go to the best loss, you can find many optimal solutions. No, did you experience that there are like 1,000, 10,000 combinations of your highly flexible model, which all more or less come to the same local minimum?
I think when it comes to this being sure that it always does, I think we can only make very limited claims here. But are you referring, just to, if I understand you correctly, are you referring to this SMAC situation where you had a lucky starting point, or what are you referring to?
The question is, are all the parameters then the same in the end?
Yeah, That's not the parameter.
Yeah.
No, the parameters are not the same, but if the loss is still
probably a major limitation here because we did not include into the study then like a evaluation of the hyperparameter space, how the algorithms moved actually. It's just the benchmarking that we're focusing on. So yes, it's more work to be done here.
Yes, here on the floor. Thanks for the talk. What is your take on genetic programming as far as optimizing hyperparameters? Because you actually mentioned Teapot, which does that. So, what's your take on that?
Yes, this would be the part where we left off here. I'll just go back to connect nicely here. Where we left off here, and we've seen that random search is throwing away all the information and then draws the next random hyperparameter to test. Now you can, at this point, you can improve several ways. The sequential model-based optimization takes all the points here. Local search, I don't know if you're familiar with local search, would just take maybe the best one and then start searching from there, which I think is a waste. I did this before in my work, and I think it's also a waste of information. And they're genetic algorithms. They work very nicely. They have big advantages as being very simple and very robust in different problems. They work with this generation. You say, after this first generation of nine hyperparameters, maybe only the first three, the best three ones, maybe somewhere here, they should survive. I throw away the rest. And from the best three ones, these ones I recombine and then mutate them a little bit. I'll be afraid that you might also throw away just a little bit too much information there, but maybe not. You would have to probably you have to start benchmarking these two things against each other. Again, Teapot is a good library to explore if that works. Thank you.
Here. Yeah, there. At the back. Yeah. Thanks again for the talks. Just to be sure I get it right, so you still need to sequentially search each hyperparameter. So let's say if you have n of them, you fix n-1 and optimize 1. Right?
Fix 1 and optimize 1. I think with one hyperparameter search, with one time running your machine learning model, you set each of the n parameters to one value, and then you run your machine learning model once. Yeah. So you have one more. In this n-dimensional space, you have one more sampling point. So you don't have to sample these n hyperparameters separately, but at once, right?
Okay.
Okay, cool.
Thanks for the great talk. I'm a big fan of all of this, and I really like Teapot, just like Teapot is a great tool.
Yes.
And I mean, there's also like auto-escalern, which automates all of that.
Yes.
And I think it's just important to stress that like the model parameter is just like another parameter, right? It's just another hyperparameter. The model you choose is just another hyperparameter, basically. And there's also a nice cool tool called Hyperband, which I can highly recommend. Hyperband is great. Just more comment, like great talk.
Yes, thanks for that comment.
Yeah, thank you. Could you comment maybe a little bit on what changes or how the approach changes if you scale up the order of magnitude of number of hyperparameters, if there's anything different having 2 or 2,000 hyperparameters?
We go to this comparison here. I think the tree structure parsing estimator, I think this one scales very nicely because you don't have to model as with the Gaussian process what you would do. Usually you don't have to, but you would usually build one model over this n-dimensional space of hyperparameters. And if it has many dimensions, that becomes slow. Usually if your machine learning model is even slower, you're still well off. And this is the general rule of thumb, that whatever you do there, your machine learning model will be slower, but doesn't have to be at some point. So when it comes to scaling, first parameters, and also the history of hyperparameters that you know about, this one scales very nicely. And the Gaussian process, I think it's scaled, but you have to correct me, I think it scales nicely with the number of hyperparameters, but with the length of the history of hyperparameters you have, I think there's like a cubic increase in computational cost, but I'm not 100% sure.
Yes. Okay, we just have time for one last question. So there was somebody in this row? No? Okay.
Hi. So in your sequential model-based optimization, you use a fast ML algorithm as your proxy for the slower ML algorithm.
Yes.
Do you validate that the hyperparameters that you found testing on the faster algorithm are also optimal for the slower algorithm? Is this assumption validated?
Yeah. We could have varied the hyperparameters. We could have varied the hyperparameters on these faster proxy models. 3 types we see here. What we did instead, we used the standard settings of the Python libraries. So we just wanted to see if they, out of the box, can do a good job. Because tuning this Gaussian process, I think it would be a bit harder. We tried it, and then we failed, and we stopped doing that and stick to the default setting, which worked better.
Okay, so thank you very much. Very interesting talk.
Thank you.